Students, welcome to lecture number 11. So, we are going to start a new topic today. We have discussed about it in the last lecture, but we are going to elaborate it in more details. So, this is about getting started with ML models and applications. So, here we are going to focus on very important ML models. As you know, I have already discussed some of the models as a part of the earlier lectures, but we are going to discuss more such models here. So, what are the things we will discuss? First, we are going to start with linear models like regression. And as you know, I have already discussed about regression, about linear regression, nonlinear regression, everything except maybe the logistic regression, which we will do today. And then we are going to discuss about decision tree, what is known as a DT here. Okay. So, what is known as a DT here, that is what we are going to discuss today. And as I told you earlier, that Bayesian aspects, that is the probabilistic aspects, I have already discussed in your earlier lecture. So, I am not going to do it here. So, we are going to discuss linear models, mostly the regression model, and then we are going to discuss SVM, DT, neural network, clustering. Finally, we talk about model selection, visualization and transformation. So, that will take about 5 to 6 lectures at least, if not more. So, we will focus mostly one model at a time. Okay. Please think about it, one model at a time, that is what we are going to discuss. And basic idea is to build in lot of these models, so that we never make any mistakes in implementing the models. So, first let us talk about a little bit about what we learned in the last lecture. Last lecture we learned about ensemble learning. Ensemble learning means it is the art of combining a diverse set of weak learners. Let me reiterate, it is basically art of combining diverse set of weak learners, so that we can improve the stability and the predictive capability of the model. In very simple form, we basically combine what? All the prediction collectively and do that, but we never do like that. We always think about taking voting, or take the best possible situation in terms of voting, right. We can always take average of that, but that is not a best way to doing the things. It is better to take measure of voting at the end of the predictions from different models, and finally, whichever is the majority voted model, we call as consider the predictions of that models or those models. Remember these aspects. In fact, ensemble models can be incorporated in both large data situations or even big data situation, as well as very small data situations also. We do not need to worry about the amount of data, that is another important aspects, because here we are basically combining different kinds of weak models. So, we can do that, we can always take both large data as well as small data problems and select different models based on how much data we have with us. The two important aspects which makes ensemble modeling distinctly different from the other model, first is the performance. An ensemble model can make better predictions, that is obviously, because we are going to use host of models. So, it is going to predict much better situations, and it can achieve even much higher accuracy in terms of predicting things compared to single contributing models. That is why ensemble model is more widely used nowadays, and informatics and ensemble model is more important than in machine learning. Okay. That is why I discussed something of these at the this juncture of the course, so that you can understand that such a kind of thing exists in the machine learning domain, and which can be used for better prediction. And these models are very robust, because they reduce the speed and dispersion of the predictions and the model prediction and the model performance. They are very robust. So, therefore, you do not need to worry much about this. Three types of models we discussed, but let me tell you, I have not discussed much about stacking. I focus my discussion on bagging and boosting models, and most important aspect in all this model is a bootstrap. Bootstrap is very powerful statistical method that eliminates basically that estimate quantity from a data sample. This is basically what I mean to say is that bootstrap is what? You divide your data into n subsets. Now, we can actually exchange data from one subset to other subset. Some rows of the one subsets will be replaced by the some rows from the other subsets, and then you can apply the models. In this way, you can remove what is known as a bias, data bias, okay, which is a very typical problem in machine learning or material science, the data bias, okay, because many cases you might be collecting data from one set of sources, or you may be generating data by some calculations or by simulations, right. So, there is a chance of biasness of the data. In that sense, this can be easily taken care of by doing bootstrapping. So, we divide total data into n number of data, and then in some of these data sets which you have created, we can replace certain columns with some other data sets, and this is can be done vice versa. So, hence it can take care of very easily biasness of data. Easiest way of doing this is to take some descriptive thing like a mean or standard deviation, okay, you can always do that also. So, in boosting what you do? Very simple, it is basically set of models connected in a series of way, okay, and this is taken for gigs.org. So, it basically separates the data into different subsets, as you can see here, C subsets, and on each subset we apply some best models. Best model means some model, maybe regression, a support vector machine or decision tree, whatever, and then we get a predictions of that. Finally, by using majority voting, we can predict the final outcome. But as you can see here, this right hand side of the slide shows even much better aspects. We can use different learners from G1 to GM, and basic idea is that learner G2 will learn from G1, whatever mistake has been done by G1 will be taken care by learner G2, and it goes forward. That is the first point. Second point is you can use weights, right, alpha 1, alpha 2, alpha 3, alpha m are weights. So, you can then at the end sum it over J1 to m alpha j Gj, where Gj are actually learners, base learners, alpha j are the weights. So, by putting weights, you are basically making or giving preference to certain kind of models which are coming a later part of this series. Okay. So, two aspects, one is the later models will learn from the mistake from the earlier models, second is these weights which are provided on these models. So, and another case is basically boost is to put these models in a parallel connections, just like electrical circuits we can have series and parallel connections, here also you can do that, you can see that. So, data sets 1 goes to learner 1 and the predictions, data sets 2 goes to learner G2, and they are then parallelly connected. So, finally, we get ensemble learning as 1 by m j I to m G j. Okay. Here we are not putting any weight factors, you do not need actually weight factors, because you are doing a parallel sequencing of the models. Okay. So, boosting algorithms are actually they are always some low classifiers or low accurate classifiers to create high accurate classifiers, or it can be any model actually, and this is done by building a model from training data, creating a second model that attempts to correct the errors for the first model. Okay. They are these models are less affected by overfitting, remember this, which is very common in regression. Stacking is little different, you have subsets of data, you can put different models and then you can combine these predictions in terms of meta learner. That is what is the difference from the boosting or pegging models. So, there are different types of boosting models we discussed, AdaBoost and gradient boosting models. AdaBoost is basically what it basically called adaptive boosting, and in this case it is simply what is done. Let me go to the next slide. So, let us say we have original data like this, it is a mixture of different colors of balls and you want to classify them. So, initially first learner will classify like this. So, it clearly sees that there is a lot of error. There is one blue ball, there are 5 green balls, all the red and other balls are removed, but second classifier will take care of that and put more weights on these green balls, so that they can be removed, right, and it goes on like this. So, that is what happened. So, we adjust weights from the initial classifier and we basically do that, so that whatever misclassified objects in the step 1 are done properly, and you can in step 3 you can further adjust it. whatever mistake has been done in steps 2, we can take care of by putting higher weights to ensure better classifications, and this way you can build a strong model. So, as you can see, it is like a gradual learning process. That is what we human are used to, right? We always learn in a gradual way. We make small mistakes in the process. At the same time, by learning from the mistakes, we can become stronger in terms of learning, and this is what is used in ensemble model learning. So, gradient boosting uses basically I told you, right, very important concept which is known as a gradient descent algorithm. It combines multiple weak learners to create a strong predictive model, but one important difference is this: it uses basically error functions reduction or reduces the error directly by optimizing the loss functions. Loss function can be mean square error or entropy error. So, what does it do? Each iteration this algorithm computes the gradient of the loss function. We talked about gradient descent problem earlier with respect to prediction provided by training a new weak model, and these predictions of the new models are then added to all the model predictions and process repeated until stopping criteria is met. Okay. And I do not want to get into a gradient descent model further, because this model actually used to find the lowest point of a hilly area by walking down the slope step by step. That is what they are learning. Okay. So, you go by step, but you always walk down the slope, and in the process actually you reach the bottommost point of the lowest point of the hill. So, you need to follow the steepest descent path, so that you can reach fast. That is the idea. So, step 1, start at the top, begin at the top of the hill, starting with random guesses at the model performance. Steps 2, you feel the slopes, simply calculate the gradient, and then you find which is the steepest downfall. Step 3, take the step, so that you can reach faster, right, and step 4 is a repeat. Okay. So, this model is basically learned for minimizing the loss function. Gradient descent actually allows you to do that. So, there are different types of errors you can calculate: mean square error, cross entropy error, hinge loss. So, gradient boosting actually does the same way. You initialize the model, start with some simple model like regression, calculate the residuals or the difference between prediction as well as the actual values, and then fit with the new weak learners. That is what it do, and then update the model every time. So, this is the main process, and then this 2 to 4 or 4 to 2 rather are repeated. This is exactly shown here. You can see there is XY data. We train using a tree 1, predict it, and this is the residual calculations. The residual is feed here again X R1 residual, and this again these data are fed into the T2. T2 will predict the data much better way. So, residual actually gets reduced, but again we use the same residual X R2 and do the similar process and keep doing that. Very interesting, right. So, this is the way actually you can achieve much lower error, or you can minimize the error as much as possible, and that is the way to achieve higher accuracy. So, let me get back to the whatever we are discussing. So, in this we are going to talk about firstly linear models. Okay. And as I told you, linear model is what we are going to discuss. So, before we discuss the linear model, this is how we are going to do. First, we will take some problems from different material domains, data sets basically, maybe physically describe the model, and then we will talk about little bit about Sky-Skid learn process, which you require for Python based modeling. And linear models, most important linear model is a linear regression, which we have discussed a lot, right. Linear regression. Then we also discuss about L1 operator, L2 operator. L1 operator is used for the lasso, L2 operator is for ridge regressions, but in thing which we are going to focus more on is this one, the logistic regression, okay, today. So, problems of material science, there are many problems which has been dealt in past, but from the data, from the experimental data, people have found out correlation and develop a equation or model, right, but we never think about it. Important aspect is in this kind of machine learning models, we need to find out the physical description of the problem, so that physics of the problem will come into picture, and we can understand the physics of the problem once you get an equation out of the data fitting. That is what I am trying to mention. So, let me elaborate it further. Let us say I have an experiment, or I have done many experiments, I have got a lot of data. Now I am fitting this data using some machine learning model. So finally, at the end of the day, I get an equation. Question is this equation physically valid? Is it capturing the physics of the problem? That is the key aspects. Then you can actually discover new aspects, because fundamentally speaking, whatever happening in the material either is because of chemistry, chemical nature of the material, or because of physical process happening in the material. So these two are the fundamental science. Now data fitting is not obviously a fundamental science, but data fitting can make our solution, or rather make us reach the solution faster, which is much faster way of reaching the solution. But that does not mean that we forget the physics. We do not understand what is happening in the material, what are the basic laws of material which are followed or not. We do not do that. So therefore, as you know, we need to use the domain knowledge. That is what I want to stress upon. Your knowledge base on your subject is very, very important, and that comes the center of these discussion. So you can have databases, you can do data pre-processing, fit a machine learning model, evaluate the model, do experiments, test the model, everything you do. We all are going to do that, but whatever we are getting at the end of these circle, is it valid when you use domain knowledge? If it is not, then this data fitting is giving you something which is not useful. That is what you should be careful about it. So let me talk about some of the models, few examples. First one I am going to talk about is Hume-Rothery models. Okay, all of you may know that this classical work of data driven formula tells you the rules for substitutional solutions. Solutions are very common in material science, right? You add carbon into iron, it forms solution of iron carbon, as well as it can form iron carbide Fe3C, right. So one is a solution, it can be alpha, gamma or delta. Other one is the carbide phase Fe3C. The solutions are very common. You can take consider brass, which is nothing but a solution of copper or zinc in copper, right, alpha brass, beta brass. Okay, these are used as a utensils. You can talk about bronzes also. You can talk about many such super substitution solutions exist. By the way, carbon in iron is not a substitution solution, it is interstitial solutions, because carbon is much smaller than iron. It goes to the interstitious or interstitial positions of the lattice or the crystal structure of this position, the location. That is why it is called interstitial solutions. But brass, bronze or titanium alloys and many other alloys, they comes under the substitution solution. Hume-Rothery provides us the rules which are again data driven. So for formation of some substitution solutions, what are the 4 rules? First is the atomic size factor. It states if the relative difference of atomic diameters between the solute and the solvent is less than 14%, then only substitution solutions are favorable. So you must be thinking where from this 14% number is coming. This number can be arrived simply by looking at the physics. You may put atoms inside the lattice of some other atom, or you can put solid atoms inside lattice of solvent atoms and then calculate how much is the maximum it can allow, because the moment you are putting a different size atom into a solvent, it is going to produce strain, it is going to put a lot of strain, it is going to distort the atomic bonds nearby. So how much of this distortion may be allowed? Hume-Rothery says maximum 14% difference can be allowed. That can be obtained from data driven approach also. But look at the physics, it captures the physics of the substitution solution. Second factor is called electrochemical factor. That means what? The solutions are possible if the electronegativity differences between the two elements is less than 0.4. You know, if the electron differences are very large, then they are likely to form compounds. Let us talk about sodium chloride. Sodium and chlorine has a huge electronegativity differences. So they can easily form an ionic bond and make a strong compound, right. That is not the requirement here. We want to form a solution, and that is substitution solutions. So we must avoid compounds. Compounds are not at all desirable. So one way of reducing this compound formation is the electronegativity differences between these two metals must be as small as possible. Here even Universally said it will be ideally less than 0.4. You can calculate that from the data driven approach. I am not doing it, but you can do yourself. A lot of data exists on solid solution formations. Third, relative valency factor. The lower valency is more likely to dissolve itself into on the higher valency as vice versa. The valency is what? Number of outside electrons, outermost cell, right? If the valency is difference is large between two elements, they are unlikely to form solid solutions, because then what will happen? There will be electron transfer from one element to other element, correct? That will lead to compound formation. That is all, this is not allowed. And last thing is crystal structure of the elements should be same or similar, because if crystal structure are different, you cannot replace one atom by the other atom. Solvent atom cannot be replaced by solid atoms easily if the crystal structures are different. So, these four factors are physics driven and physics related, and we can we can think about they can be obtained from data driven analysis of the different analysis. Obviously, when Hume authority discovered these rules, not many solid solution exists in 1923 sometime, exactly I do not remember in those times. So, in those days this kind of concepts are not there. So, he actually looked at the physics of the problem and then discovered this set of rules. Second problem is the Ferris law of fatigue crack growth. Ferris law is very important in fatigue. Fatigue, if you apply what kind of cyclic loading, fatigue happens, fatigue failure happens. Many of the objects actually undergoes this kind of cyclic loading. And so, Ferris law states that fatigue crack growth is low power functions of applied range of stress intensity factors. Let me explain to it. So, this is the equation dA by dN is equal to C into K to the delta K to the power m. So, here dA the change of crack length, n is the number of cycle, change of cycle. So, A is crack length, n is the number of cycles, delta K is the difference of stress intensity factor. You may know, may not know, right? It is related to fracture toughness. Okay. Now, this was also determined purely by data. You can clearly see this is what is log of dA by dN, this is log of delta K. So, if I take a log of this, so this will be a straight line equation, right. That is what you see at the center of this position in the regime B, is basically becomes a constant slope. So, Ferris law is very much valid in the central portion of this diagram. Remember, this is widely used in the industries and academia, because fatigue is a major mode of failure of materials and the structures. That is why this is an empirical relationship looks like, but no, this is a purely physics based relationship. It can be obtained from data science, it can be also obtained from theoretical calculations also, because crack propagation depends upon the stress intensity factor and the crack, right. So, basically once a crack moves in the material, this is what is the fine tip of the crack, there is a huge stress built up here in the front of the crack, correct. So, difference is the delta K is nothing but a difference with stress intensity factor when crack tip was present minus when the crack tip was not there. That is what is delta K is. So, delta K can be used as a prominent factor for the fatigue crack growth, and m is an exponent obviously, and you can understand the whole thing depends on the m. So, when you make a log of that, m comes out from the log. So, if you take a log of this, log of C plus m log of delta K. So, because this is a plot between log of dA dN versus log of delta K, the slope of this curve is basically nothing but m, right. So, that is why it is a straight line equation. The last example is what is called Hall-Page equation. This is very important equation in material science, right. It provides you gain side dependence on the strength of the polycrystalline material, especially yield strength. And this is how it is written: yield strength is equal to a constant stress, yield stress is equal to constant stress sigma I plus k d to the power minus half, where k is a constant again and d is what is your grain's diameter, right. This is extremely important in the to the entire metal industry, because most mechanical properties except for few like keep resistance will be enhanced by simply reducing the grain size into a sub micrometer or nanometer level, right, very very important. So, this equation can also be fitted using data science, but this is a very fundamental equation. This happens because of grain boundaries. As the dislocation moves from one grain to other grain, grain boundaries act as obstacle for the motion of dislocation, and this is what is known as a grain boundary strengthening. So, that means by making polycrystalline grains compared to single crystal, I can increase the strength of the material. So, as you understand, these are the factors, the important aspects, or some of the examples of the how data driven discovery of theory of models are possible. These were not done by data driven, okay, by the way, although Hall and Page did many experiments, but they tried to understand the physics, what is happening in the material, and that is how they discovered this path picking important mathematical expressions, which has changed the dynamics of material science. There is a Paris law, Hume-Theory law, or Hall-Page equation. Okay. So, let me stop here. We will come back in the second part, talk about scikit-learn as well as the linear models, mostly logistic regression and something more also. Let me come back. Okay.